Annealing and annealing furnaces in semiconductor industry. Annealing is a critical heat treatment process widely used in semiconductor manufacturing to modify the properties of materials after implantation, deposition, or etching steps. In this context, annealing serves three major roles: heat treatment, manufacturing optimization, and control of crystal structure. As a heat treatment, it is used to repair damage in the silicon lattice caused by ion implantation and to activate dopants, ensuring electrical functionality. In terms of manufacturing, annealing enhances performance characteristics like carrier mobility and junction depth, supporting the production of high-performance transistors and integrated circuits. Lastly, annealing helps manage the crystal structure by relieving internal stresses and restoring order in the atomic lattice, which is essential for maintaining material integrity and electrical properties. Understanding annealing and the furnaces used to carry it out is vital to grasping how modern electronics achieve their speed, efficiency, and reliability. Semiconductors, the building blocks of modern technology. Semiconductors are materials with electrical conductivity that lies between conductors like metals and insulators such as glass. This unique property allows them to be finely controlled, making them essential for electronics. Silicon is by far the most commonly used semiconductor material due to its abundance and excellent electronic characteristics. One key feature of semiconductors is that their electrical properties can be precisely tuned through a process known as doping, which introduces specific impurities into the crystal structure to control conductivity. These materials are found everywhere, inside smartphones, computers, vehicles, LED lights, displays, and solar cells. Their significance stems from their ability to enable the digital revolution, allowing precise control of current and voltage in circuits. Key properties include conductivity control, crystal structure stability, sensitivity to temperature, and doping capability, all of which are essential in the performance and functionality of modern electronics. What is annealing? Annealing is a controlled heating process used in semiconductor manufacturing to alter the physical and electrical properties of materials. This heat treatment typically involves heating materials to a specific temperature range, usually between 400 degrees Celsius and 1200 degrees Celsius, followed by holding and cooling. The main purpose is to relieve internal stresses, activate dopants introduced during implantation, and improve the overall crystal structure of the material. The annealing process includes three key steps. First, heating raises the temperature rapidly to the target level. Second, holding maintains that temperature for a precise duration to allow reactions to occur. Finally, controlled cooling gradually reduces the temperature to avoid thermal shock or defects. The temperature profile follows a distinct pattern of rapid rise, stable hold, and a carefully managed cool down. Annealing is critical because it reduces stress, enhances material properties, activates dopants, and improves the crystalline structure necessary for optimal electronic performance. Why annealing is critical? Annealing is essential for ensuring the performance and reliability of high-performance semiconductor devices. Without annealing, several issues can arise. Crystal defects may remain in the silicon lattice, reducing electronic performance and reliability. Inactive dopants, introduced during ion implantation, may not become electrically active, leading to malfunctioning devices. Internal stresses from prior manufacturing steps can cause structural weaknesses or even device failure. Additionally, poor interfaces between layers can compromise electrical connectivity and device efficiency. In contrast, annealing solves all of these problems. It creates perfect crystals by repairing defects and improving atomic structure. It ensures active dopants, with 100% activation rates often achieved. It provides critical stress relief, eliminating stress introduced during fabrication. And finally, it results in strong interfaces with excellent layer-to-layer connections. Altogether, annealing is not optional. It is a foundational step in producing high-performance, reliable semiconductor components. Why annealing is critical. Performance impact. Annealing plays a vital role in enhancing the overall performance of semiconductor devices. Without annealing, devices suffer in multiple ways. They may operate with slow performance due to crystal defects and inactive dopants. Power consumption tends to be high because charge carriers do not move efficiently through the imperfect structure. These factors also contribute to frequent device failures and low long-term reliability, leading to poor customer satisfaction and yield loss in manufacturing. On the other hand, annealing enables significant performance gains. It improves speed by optimizing electrical pathways within the silicon, and it reduces power consumption by enabling better charge mobility. Reliability is increased because the process relieves stress and repairs structural damage. Additionally, manufacturers experience better yields, meaning more functioning devices per batch. Overall, annealing can improve device performance by an impressive 10 to 50%, making it a cornerstone of high-performance semiconductor fabrication. The annealing process. The annealing process is a critical thermal treatment step in semiconductor manufacturing, involving 5 main stages that transform wafer properties by precise heat control. First is wafer preparation, where clean wafers are carefully loaded into the furnace. Cleanliness is crucial to prevent contamination that could compromise device performance. Next is ramp-up heating, during which the temperature is gradually increased at a controlled rate, typically 5 to 20 degrees Celsius per minute, to avoid thermal shock and ensure uniform heating. The third step is the anneal hold, where the temperature is maintained steadily, usually between 800 to 1000 degrees Celsius, for a fixed period, often 10 to 60 minutes, allowing atomic restructuring to occur. Following this is controlled cooling, where the temperature is reduced gradually, at a rate of 1 to 5 degrees Celsius per minute, to prevent defects caused by rapid cooling. Finally, in wafer unload, the processed wafers are removed, completing the annealing cycle. Annealing process. Key parameters. The success of the annealing process depends on careful control of several key parameters. Temperature is one of the most critical, typically ranging from 400 degrees Celsius to 1200 degrees Celsius, depending on the materials and desired outcomes, such as dopant activation or defect repair. The time for annealing also varies with temperature, usually lasting between 10 and 120 minutes. Shorter times are used for high-temperature anneals, while longer durations apply at lower temperatures to ensure uniform thermal diffusion. The atmosphere within the furnace must be controlled using inert gases like nitrogen, N2, or argon, Ar, to prevent oxidation or contamination during the high-temperature hold. Pressure is usually maintained at 1 atmosphere or ambient pressure, which simplifies system design and avoids additional stress on wafers. Overall, the total cycle time, including ramp-up, hold, and cooling, can range from 30 minutes to 3 hours, depending on the specific process and wafer requirements. Types of annealing furnaces. In semiconductor manufacturing, 3 main types of annealing furnaces are used, each offering distinct advantages for different production needs. Batch furnaces are designed for high-volume processing, handling 25 to 200 wafers simultaneously. These furnaces operate at temperatures between 400 degrees Celsius and 1200 degrees Celsius, making them ideal for dopant activation. They offer high throughput, are cost-effective, and provide uniform heating across large wafer lots. Cycle times typically range from 1 to 4 hours. Rapid thermal annealing, RTA systems, are tailored for fast, single-wafer processing. They reach temperatures up to 1500 degrees Celsius with extremely fast heating rates, around 200 degrees Celsius per second. This allows precise temperature control and minimal dopant diffusion, making them ideal for spike annealing with cycle times of just 10 to 60 seconds. Lastly, tube furnaces support continuous processing in horizontal or vertical configurations. Suitable for 5 to 50 wafers, they provide medium volume processing, excellent uniformity, and are commonly used in CVD and oxidation applications with cycle times of 30 to 120 minutes. Annealing furnace performance comparison. Choosing the right annealing furnace requires balancing several key performance factors: throughput, process speed, and operating cost, based on specific production needs. Batch furnaces offer high throughput, processing large volumes of wafers simultaneously. However, their process speed is slower due to longer heating and cooling cycles. Despite this, they are cost-effective to operate, making them ideal for high-volume, budget-conscious operations. Rapid thermal annealing, RTA systems, in contrast, provide very fast process speeds, with heating rates that enable precise thermal control and minimal dopant diffusion. Yet, they have low throughput as they handle wafers one at a time and come with higher operational costs. Tube furnaces fall in between, offering medium throughput and medium processing speed. Their operating costs are also moderate, and they are well suited for continuous operations like oxidation and CVD. Ultimately, furnace selection depends on required volume, speed, precision, and cost considerations for the given process. Rapid thermal annealing, RTA. Rapid thermal annealing is an advanced single-wafer processing technology used for high-speed thermal treatment. The core of RTA lies in its technology. Heating is achieved using powerful infrared halogen lamps, which deliver an impressive ramp rate of 200 degrees Celsius per second. Real-time monitoring is performed using pyrometry, enabling closed-loop control to ensure precise temperature accuracy. RTA operates under controlled atmospheres, typically nitrogen, argon, or vacuum, to ensure a clean, contamination-free process. The timing is extremely short, typically lasting only 10 to 60 seconds, ideal for spike annealing applications where minimal diffusion is critical. RTA is widely used across multiple applications. For dopant activation, it effectively activates implanted ions in source, drain regions, gate structures, wells, and halo implants, all without causing unwanted dopant diffusion. It's also critical for silicide formation, enabling low-resistance contacts using titanium silicide, nickel silicide, cobalt silicide, and platinum silicide. Additionally, in metal processing, RTA supports crystallization and stress relief in films, useful for copper and titanium contacts, aluminum reflow, and tungsten plugs. Rapid thermal annealing, RTA. Rapid thermal annealing, or RTA, is a crucial single-wafer processing technology used to enable precise thermal treatments in semiconductor fabrication. One of the biggest advantages of RTA is minimal diffusion. Since the wafer is exposed to high temperatures only for a very short time, dopant atoms don't have much time to move, preserving junction depth and profile. RTA also offers precise control. Temperature ramps and durations can be finely tuned, enhancing uniformity and repeatability. Processing one wafer at a time allows optimization tailored to each wafer's requirements. RTA also achieves low contamination due to reduced contact and better environmental control. Typical processing temperatures range from 800 to 1500 degrees Celsius, with specific windows for dopant activation, silicide formation, and metal processing. The process time is short, typically between 10 and 60 seconds. Heating and cooling rates can reach up to 200 degrees Celsius S and 100 degrees Celsius S, respectively, supporting fast thermal cycling while maintaining device integrity. Applications and benefits. Annealing plays a crucial role in enhancing the performance and reliability of modern semiconductor devices. One of the key benefits is improved performance. Annealing helps activate dopants and repair crystal damage, leading to faster switching speeds and more energy-efficient devices. Reliability is also enhanced as annealing reduces crystalline defects and other imperfections, directly contributing to longer device lifespan and more stable operation. Precision is another critical gain. Through exact control of thermal conditions, annealing enables accurate dopant activation without unwanted diffusion. Structurally, annealing restores crystal order by repairing damage from implantation processes and optimizing lattice alignment. This restoration is essential for ensuring proper electrical behavior. Lastly, yield is significantly boosted. With fewer defects and improved process control, the overall success rate of wafer production increases. This means more working devices per batch, ultimately enhancing manufacturing efficiency and reducing production costs across the board. Applications and benefits. Key benefits of annealing by device type. Annealing delivers targeted performance enhancements across different semiconductor applications. In processors like CPUs and GPUs, it supports source and drain activation, gate formation, and contact solicitation. The outcome is higher clock speeds, reduced power consumption, and enhanced transistor behavior, delivering an overall performance gain of about 25%. For memory devices such as DRAM and flash, annealing helps with cell formation, barrier layer construction, and interface optimization. This leads to faster data access, higher storage density, and better data retention, contributing to a 40% improvement in speed. Power devices, including IGBTs and MOSFETs, benefit through applications in high-voltage components, power management, and electric vehicles. Annealing in this context improves efficiency, enhances thermal handling, and reduces switching losses, resulting in a 15% efficiency gain. Finally, in RF and wireless applications like 5G and IoT, annealing enables better performance in GaN/GaAs devices, amplifiers, and antenna switches. The benefits include increased frequency response, superior signal quality, and reduced noise, leading to a 30% frequency boost. Applications and benefits: annealing in imaging, energy, lighting, and automotive devices. Annealing brings powerful advantages across a wide range of modern semiconductor applications. In CMOS imaging sensors, it improves pixel structures, enhances color filter array performance, and optimizes low light sensitivity. These changes result in better image quality, increased sensitivity, and reduced noise, achieving a 50% gain in sensitivity. For solar photovoltaic devices, annealing supports junction formation, defect passivation, and contact optimization. These improvements lead to higher power conversion efficiency, improved current collection, and reduced recombination losses, contributing to a 20% energy boost. In LED devices used for displays and lighting, annealing activates GaN materials, fine-tunes color output, and enables quantum well formation. This enhances brightness, color purity, and lifetime, leading to a 30% gain in advanced functionality. In the automotive sector, annealing enhances the reliability of ADAS processors, motor controllers, and safety sensors. It improves temperature tolerance and ensures functional safety, resulting in a significant 60% increase in system reliability for critical automotive applications. Future trends and conclusion. Annealing technology is evolving rapidly to meet the demands of next-generation semiconductor devices. Emerging technologies include laser annealing, which delivers ultra-fast, localized heating using nanosecond pulses. This allows precise treatment of selective wafer regions, improving device performance without affecting surrounding structures. AI and machine learning are revolutionizing process control through predictive models and real-time adaptive adjustments, enhancing yield and reducing variation. The industry is also shifting toward new materials beyond silicon, such as GaN, SiC, and 2D materials, which require customized annealing profiles for optimal performance. These advancements align with Industry 4.0 trends. IoT connectivity enables real-time monitoring and control. Big data analytics provide actionable process insights. Automation supports full system integration, and cloud integration allows for remote operation and updates. Key takeaways include annealing's critical role in modern manufacturing, the precision enabled by RTA and advanced furnaces, its wide application range from CPUs to solar cells, and future growth driven by AI, sustainability, and material innovation. Future trends and conclusion: growth, sustainability, and innovation. The future of annealing technology is marked by strong growth, greater sustainability, and advanced innovation. The market size is projected to rise from $1.5 billion in 2024 to $2.8 billion by 2030, reflecting a robust compound annual growth rate of 7.5%. This signals strong industry confidence in the continued importance of annealing. On the sustainability front, advanced heating technologies are expected to improve energy efficiency by 30%. Cleaner materials and processes are predicted to reduce CO2 emissions by 25%, while better yield and recycling strategies will cut waste by 40%. Annealing remains central to semiconductor progress, supporting faster, smaller, and more efficient devices. As chips become increasingly complex, intelligent annealing systems will be vital. The innovation roadmap highlights AI-driven process control between 2024 and 2025, widespread adoption of laser annealing by 2026-2027, and advanced material processing from 2028 onward. Indeed, annealing is powering tomorrow's technology, today.